welcome to my talk. We'll be talking about type proofs, which eventually allows us to encode our own type system features into Kotlin. Type proofs are written with Arrow Meta, a meta-programming library that interoperates with the Kotlin compiler at any step throughout the compilation process. And eventually, what we'll see in the next 20 minutes is how we encode ad hoc subtyping in Kotlin, union types, refined types, inductive proofs, and type classes. And then the cool thing about type proofs is that we don't have to change the grammar or semantics of Kotlin to achieve all of this with a powerful machinery like type proofs. It was mentioned, my name is Imran Settuba. I work at 47 Degrees. I'm one of the Arrow maintainers in Kotlin. Who here knows about Arrow or heard about it? Awesome. So Arrow is the functional companion to the standard library in Kotlin, and Meta is the functional companion to the Kotlin compiler and the IDE. A disclaimer, all the Arrow plugins that are out there in our project are not finished yet and completely working. We're working on that heavily and are working on an alpha release in April. Before we go into type proofs, we might as well look into how the type hierarchy in Kotlin looks like, and for that, I made a small diagram. Nothing is our bottom type in Kotlin. We have any and any nullable, which is our top level type in Kotlin, and everything that the user describes, whether these are built-in types or types that you declare, are essentially in between any and nothing. Now, at a more granular perspective, type proofs are nothing else as an implementation of the Curry-Howard-Lambda correspondence. In this talk, we'll be looking at it as this, that there is a correspondence between type theory, closed category theory, and essentially logic. Sorry. And what type proofs allow us to do is to eventually write those proofs into the Kotlin type system. Now, what we also did is that the type checker is proof aware and allows us to interact with the IDE, allowing us to get type resolution out of the box. Later, we'll be seeing some demos how that looks like from a user's perspective. Now, what proofs also allows us to do is to create relationships between types without inheritance, simply through a proof. And when we look at inductive resolution, it is nothing else as whenever we have a proof from A to B and B to C, the compiler should be able to generate a type proof from A to C. Now that has a few limitations and pain points we'll be going through later. But we essentially want that, for instance, whenever there is a proof between a person, which is just a data class, and that's isomorphic to a record type, and there's a proof from the record type to an H list or a tuple, then we also want, and we also have a proof between a tuple and an encoder in JSON, that we should, the compiler should give us the APIs of the JSON encoder. Now let's look at ad hoc subtyping. Now here we see a person which has a name and an age and a tuple. And in our example, the compiler can type check that the person is a tuple and also isomorphic to its own type. And we achieve that simply through an extension proof. And we set the implicit coercion as true. So, and the proof sample is pretty simple. We put the name and the age into the tuple, same in reverse. And with this, we still have the ability to sustain coherence, in the sense that the only thing that meta allows us to do is to have orphan overrides. That means that if you don't own the data class or the type class, you cannot export your instances. That allows us to have coherence over the Kotlin ecosystem, similar to what you see in Haskell. If there are any questions, you can always raise the hand and ask. The next thing, we can look into how we can encode union types. So our initial encoding is fairly simple. Union types have only one value, and we declare that simply through the, oh, that is very small. I'm sorry for that. So it reads that we're declaring the union of 4. It only contains one value, which we declare as the top level value that is available in the hierarchy of Kotlin. And then whenever we want to have a smaller union, for instance a union of 3 or 2, we can reuse the one from before, and through the type alias, the compiler will erase that at compile time. So at the end of the day, we only have that, the biggest abstraction. Now we can encode first and second position. That allows us to have, when we declare a union of an orange and an apple, that only apple and orange are allowed, but whenever we have a strawberry, we will get a compiler error. We get this simply through a proof by saying whenever the type is inhabited by the union, then we can provide it, and if not, this will bail. But this is not always ergonomic. So what we can do is to implement native support for nullable types, simply by defining whenever there's a type at this first position, and we know that the value exists, then we should be able to cast it down to the type. And here, this would compile, but at runtime, this will be a null value. Now, moving on. If we want to encode any properties similar to what the .calculus has, and if you look into how Meta implements the type proofs for union types, they exactly follow that style. We would go for instance, associativity. That means that a union of 2. Okay, I think everyone can read that. And associativity can be implemented simply through whenever the type A is the second of the first position, we can swap it out, and that's fine. We can also do the same thing with commutativity. And this property is one of the reasons why unions cannot form monads or functors, and cannot assimilate data types that you might know as option and either, because they are right bias. Let's move on to refined types. So type proofs also gives us a pretty much a free abstraction into defining type refinement in Kotlin. That means that we can implement positive ints by saying whenever the type that we have here, oh, there you go. Whenever we have an integer which is bigger than 0, the important thing is that inline classes in Kotlin only contain one value, and at compile time, that wrapper will be erased. So this is a zero-cost abstraction over integers. And what the compiler will generate is some refined function in its companion. And whenever positive int is subject in the compiler or user code, it will check if it is really obeying the refinement that we wrote. And here we'll see an example that one will type check fine, this will not type check, and this works for literals but not for runtime values. But we see later how we can encode that. And here you see that this won't compile because we can only check for runtime for literals. But we can extend it, our proof, simply with this here. That we can say whenever there's an integer, we can define a proof from integer to positive int nullable. Whenever it is refined, we can box it into the positive int. If not, we will just emit the null. And moving on, we can also look into other use cases where positive int can be in the user codes. Let's say we have a runtime value from the database, 1 or -1. These are just examples in that sense. This will not be okay and will not compile because we cannot just box runtime values into positive ints. But this will be fine because we already defined a proof from integer to positive int nullable. Now we can look into inductive proofs now because they're quite powerful in the sense that whenever we have a proof from A to B and B to C, the compiler will generate a proof from A to C. Now here's an example where we define a data class or a Haskell record type where we have a point from point 4 and 3 and 2 and 5, and we can combine that. But that plus only exists because tuple 2 has the notion, tuple 2 of integers has the notion of a semigroup. And we can start by declaring that isomorphism between data classes and record types, or in this case, tuples, simply by saying that we can box it, and the compiler will generate that for us for free, so we don't have to do that. And the next part is when, hang on for a second, we define the proofs for the semigroup and the semigroup from integers and tuples, simply by saying a tuple has a semigroup implementation whenever each type in its tuple has a semigroup implementation. Hang on for a second. Now, the important part is this, that we want to derive these behaviors simply by structure, and type proofs allow us to do that over co-products or product types, including data classes, shield classes that don't box primitives. Now this is where the proof ends with the compiler, because now the compiler will just reuse the existing proofs it finds for each type and ends up with the proof from A to C, and we accomplished to understand why this compiles and type checks. Now, I hope at this point you believe me that and know that we have type classes and ad hoc polymorphism in Kotlin. Okay, the video is a lot smaller now, but we can see that Kotlin brings a different way of ad hoc polymorphism to functional programming, because the member access is by subtype proof and not through dispatching over interfaces. That means that we can define proofs and relationships between type classes with proofs instead of inheritance. At this point, if anyone is interested in what we do or wants to know more about our meta, we're a very inclusive community, and if you have any questions, you can ping me or anyone in Twitter for that regard. And we have a lot more use cases in Meta than the ones that I displayed to you. One of the features are, for instance, Google-like search engines that you might know from Haskell, type holes for suggesting APIs and incomplete programs and which proofs you need to fulfill them, custom rule linters that you can have at compile time and not at build time. And we can even extend what Meta has available by providing a more advanced language prototyping landscape. But there's a lot more meta programming use cases than that. At this point, thank you for the community, for the Kotlin community, JetBrains, and everyone involved in our journey to provide all these features. Thank you.